The sun never sets in orbit. And someone is about to use that to power the entire planet.
In orbit, a solar panel receives about 8 times more energy than the highest performing panels on Earth's surface. Up here, there is no atmospheric interference, no weather, and in the right position, no night cycle. Historically, our energy extraction has been strictly tethered to the ground. We excavate fuels trapped in the crust, or we build terrestrial solar farms that sit idle half the day and lose efficiency the moment a cloud rolls in. To capture maximum output, engineers look to geostationary Earth orbit, or GEO. Positioned 36,000 kilometers above the equator, satellites in GEO experience a solar intensity 144% stronger than on the ground, and they remain bathed in sunlight 99% of the year. The barrier to building infrastructure at this altitude was always the price of the rocket. But with the rapid development of heavy-lift, fully reusable launch vehicles like SpaceX's Starship, the cost of sending payloads to orbit is actively dropping toward $100 to $200 per kilogram. At that price point, the economics flip. Launching the thousands of tons of material needed to assemble an orbital solar array transitions from a theoretical physics problem into a viable, profit-generating enterprise. Once you generate that power, you hit an engineering bottleneck. Moving gigawatts of electricity across 36,000 kilometers of empty space requires a transmission system completely free of wires. In 2023, a Caltech orbital testbed called SSPD-1 successfully demonstrated exactly this. Using an experiment called MAPLE, engineers proved it is possible to wirelessly transmit power in the vacuum of space and direct a detectable beam down to Earth. This data readout tracks signal level fading and lock-off disruptions during high-frequency satellite transmissions, highlighting atmospheric interference volatility. Scaling to gigawatt transmissions risks ionospheric heating, where the microwave beam alters the upper atmosphere's electron temperature, causing severe energy loss. To safely capture the remaining energy, the ground requires a rectenna, a massive grid of rectifying antennas spanning kilometers. These stations receive microwaves spread out to low, safe intensities that fall strictly below OSHA workplace exposure limits. Success requires threading a high-energy needle. The orbital array must push enough power through the atmosphere to be commercially viable without cooking the local ionosphere, scrambling global communications, or harming the terrestrial biosphere. Building kilometer-scale glass architecture in space exposes that infrastructure to a literal war zone. Earth's orbit is currently polluted with over 8,000 metric tons of high-velocity debris. This graph tracks orbital debris growth. The steep pink fragmentation line reveals rapid shrapnel accumulation from explosions. The massive gap between intact spacecraft and the total object count exposes the true hazard, roughly 100 million lethal, non-trackable objects ripping through orbit. A single impact can disable a satellite, creating a cloud of new debris that triggers a compounding chain reaction known as the Kessler syndrome. To protect future infrastructure, the U.S. government relies on an interagency strategy to limit new debris by design, improve radar tracking, and actively remediate existing junk. If we cannot maintain traffic control and clear the debris fields in low Earth orbit, the logistics chains required to build solar megaprojects will fail. Orbital cleanup is a mandatory prerequisite for space-based power. Back on Earth, massive commercial demand is already forming. Technology companies are negotiating agreements for orbital power to feed artificial intelligence data centers, securing a constant energy supply that bypasses the severe bottlenecks of the terrestrial grid. This demand accelerates an international arms race. China is executing an aggressive timeline to launch a megawatt-grade solar station by 2035, followed by a full kilometer-scale collector by 2040. The strategic advantage extends far beyond commercial electricity. A state controlling a geostationary solar array can weaponize its energy logistics, beaming power to an off-grid military base and instantly redirecting that beam to a remote disaster zone without relying on physical supply lines. As this map expands to show energy webs blanketing entire hemispheres, it illustrates the Space Silk Road. Supplying inescapable clean energy to developing nations builds deep geopolitical leverage. By mastering orbital manufacturing and wireless transmission, nations are competing to claim the sun. The winner secures an infinite energy source and dictates the global economic order for the coming century. Operating a power plant in geostationary orbit marks a physical transition point. It shifts humanity from a planet-bound species constrained by terrestrial resources into a civilization extracting energy on the scale of the solar system. The information presented in this video is for educational purposes only and does not constitute financial or investment advice.
The race for space energy has already begun. The question is, who wins it?